Okay, so everybody got the course webpage? What the heck is that? I thought I removed all that stuff from this computer. Just because I want to make sure that everything's working. We're recording. All right. So a couple of things. Notice that today we're going to talk more about MOS capacitances, review of RC circuits, and frequency response. When we talk about op amps and compensation, I'm going to assume you know frequency response very well in chapter 21, I think it is. So I don't want to just keep going until I feel comfortable everybody knows that. The homework you probably already saw. There's homework here. The homework 2 is A6.2, A620, and then that simulation just as seen there. Those problems are not from the book. They're from the book's web page. That's what the A means. It's additional. So if you go here and you look, go to chapter 6, these are the problems that we're talking about. Notice I don't write up the solutions for these because I found that just nowadays just about any homework problem, any textbook you get that's reasonably popular, you can download the solutions manual for without the author or publisher's permission, and so I make up my own problems and put them on there just to make sure you get a quality education. Let's see. When you email the Google group, don't email the Google group to me. All right, it kind of defeats the purpose. If I may answer, and that's fine, but email the Google group so that perhaps somebody else could answer the question. I think there's like 1,300 people on there, and I've got lots of former students. And so I'm sure some of them would get a kick out of answering questions that are there, but I'm pretty fast in answering questions if I'm not tied up doing something else. All right, before I get going back in lecturing, I want to cover some more fundamental stuff, but before I do, are there any questions? Are there any questions about the homework? I'm going to try to answer some of them I'm anticipating. All right, so let's do that to begin with so we can all start out with good grades. And so this is complicated, EE 422 and ECG 622, and it's basically analog IC design. This is going to be my last really, hopefully, trivial lecture because I'm kind of thinking that I'm going real slow and introducing the concepts, and hopefully you think the same thing. But let's look at this circuit right here. Let's say 10 picofarads, 10K, and I've got a pulse coming in here. Let's just say in, and it bounces back and forth 0 to 1. And then over here, I go ahead and I put a voltage source, and I put 10 volts there. Okay? So, if I ask you, how long, first, can I sketch the voltage there? So here's my input. And my input comes in. It goes from 0 to 1 volt. I want you to sketch the output. This is V out. Now I'm doing this on purpose because this 10 volts is kind of what you have with the MOSFET in some of the situations on one side to keep it in strong inversion. And I ask, how does it affect the voltage over here? You're not reading another class, are you? Okay. All right, just checking. Okay, so what just happens over here? What's the final voltage and why? So if I look at this, that's V out. It goes to 1 volt. So question, what if I change this to 90 volts? Does it affect anything over here? If this is 90 volts DC or 10 volts, this always stays at 10 volts, correct? Does it affect anything that's happening over here, even though I change that voltage? Now this is useful for your homework. Doesn't. It holds it right there at the same potential. So now, when you took electronics 1, and we said, this is AC ground, did you understand that? No? Okay, so this is at 10 volts and it's fixed at 10 volts. There's no way for me to vary that voltage, right? So it doesn't matter this thing's going up and down, or if it's a sine wave, or if it's a square pulse, or whatever. It doesn't, nothing changes over here. This is AC ground. And so I could redraw this circuit equivalently, if I care about this node, to just look like this. Because I don't care that that's DC at 10 volts, right? Does everybody follow? Does everybody follow? No matter how I wiggle over here, this voltage source holds that point at 10 volts and doesn't let it move around. Okay, does it make sense? Make sense? Okay, so let's go look at a similar homework problem, and I got to be careful I don't mess up things here. Okay. Let's say that I have this circuit right here. And let's say, let's draw it crazy. And I ask you, simplify that circuit for me. First off, this has some W over L. What's the capacitance of this device? Okay, so in my mind, I'm thinking of this as nothing more, as long as it's in strong inversion, we're going to cover that again, as a capacitor. So I want you to redraw this circuit in a simpler form so that I can use what I talked about before. So I'm going to redraw this over here. I'm going to put a resistor square like that. Then I'm going to come over, I'm going to put my MOSFET capacitor, but instead of connecting it, let's connect it to 5 volts. So this is source, drain, bulk. This is gate. So this is gate, source, drain, bulk. Does everybody agree? Okay, so now when I put a pulse here, assuming this capacitor stays in strong inversion, this pulse rises up like this, charges through the resistor, and I get a pulse that does this. How does that 5 volts there affect the pulse over here? Doesn't. I can put this at 10 volts. As long as it stays in strong inversion, that is. It doesn't affect anything, right? Does everybody follow that? So I don't get confused. Now, let's pause for a second. You ask, where would you use a MOSFET like this? Where's an application? In flash memory, in your thumb drives, or your cell phones, or whatever. To program the flash chips, they need high voltages, say 20 volts. But your power supply may be only 1.5 volts of battery, okay? So they make what's called a charge pump that pumps up the charge. And let me just give you a simple example. If I take, I'm not going to draw a MOSFET capacitor, but you can imagine if I do this and I put this to plus 5 volts, and is everybody comfortable at this point with thinking plus 5 volts is just a connection like this? Okay, if I look at this DC wise and I've got a pulse in here, this voltage starts out at plus 5 volts. But if I pulse this side up, what happens is this side up pulses as well, and it goes up to 10 volts. As long as I capture that, I could rectify it if you want, capture that 10 volts over here, I can use this simple topology to generate higher voltages. In your flash memory chips, what you need to do is you need 20 volts or so to write to what's called a floating gate device. So we talked about the poly over the silicon, right? So we had our N plus, P substrate last time in poly. In a flash memory, all that they do is they put another piece of poly right over that, and then this piece of poly is called the floating gate. They apply a really high potential, and electrons tunnel through the oxide back up into this floating gate. Well, when you remove that high potential, that electrons are trapped there. Whoops. Yep. If I'm used to having the screen over here, so I can see if I'm off. So if I'm not used to it being over here, so if I'm off, just go like this or make some hand movement or something, and I'll adjust, because I don't see it as well as I normally do. But when I apply a positive potential, I get electrons onto this poly, and it stores the information there. And this is what's flash memories called. And the reason it's called flash is in the olden days, 25 years or so ago, to erase the floating gate, you had to apply an ultraviolet light, which would increase the conductivity of the glass surrounding the polysilicon so the charge could leak off. Well, flash is much faster than taking the chip out, putting it under an ultraviolet light, letting it sit there for a few hours, and taking and put it back in. So that's why it's called flash, because it's programmed in a flash. So you use these MOSFETs in what are called charge pumps to generate high or low. There's some cases where you need negative voltages too from the battery. Okay, so it's not an academic thing. This is important, and I can show you some examples online if you want to take a quick look. All right, any questions before about the whole point of this was I put that homework problem and I said, oh, we got 5 volts here, and then I thought I got to make sure in class I cover that because they may think this actually matters. Then it doesn't matter for the step response. It matters for keeping this in strong inversion. And again, I'm going to cover that more in a moment. We'll review the NMOS and we'll do the PMOS. One other thing I want to talk about before we move on to reviewing strong inversion for your simulations. When you are doing your sims, let's just do the PMOS since that's the one we were just talking about. And I don't remember the exact homework problem, but it was like, this is A, and it's like, and that's my eyeball looking up, what's the capacitance I see looking up? You calculate it, oh, it's easy, Cox prime times L times W, but you want to verify it. How do you verify it with a sim? Here's how you don't verify it. If you do this, drawn the symbol wrong. You get the idea. If you do this, where this is at +5 and then you go 0 to 5, when this pulse goes up to 5 volts, you have 5 volts across the MOSFET. This is supposed to be a MOSFET here. And that's zero potential. This device is no longer attracting holes. It's no longer in strong inversion. Okay? So if I want to verify it, what I want to do is I want to put, 0 to 1 millivolt. Does it matter? No. It just matters you're going to see an RC, but the actual amplitude doesn't matter. When you go make measurements in the semiconductor industry and you try to measure capacitances with MOSFETs, they use small signals like this, measure the frequency response or the step response, and measure the delay. And that's how you characterize the capacitance of a device. It's still essentially, when you're at 0 and 1 millivolt, for all intents and purposes, it's still 5 volts across the device. But you put this little signal here, and now all of a sudden, you're able to look at the step response and measure the capacitance. Does everybody follow? Okay? All right. So, any questions on RC circuits? Yes?
Question of how you're drawing those MOSFETs. The little circle part, that's the gate, and then the big block part is the source drain and block.
Yeah, so this is the gate. and this is the source, body, and drain. Let me just, I think that's the way it is in LT Spice. Let's just take a quick look. It's not. I can't hear too well with this, so if you're asking something and I can't hear, it's muffled, and so I'm not, hopefully by the end of the semester these will get straightened out. So if I do file, oh, let's do this. Let's do file, save as, and MOS lecture 2. Did anybody download these? I was hoping you'd say no, because then I'd stop posting them. Okay, so let's go ahead and get rid of this and put up PMOS. Control R it. And then let's cheat and do this. And change that to 5. So I'm doing this on purpose so you guys can get different exposure to LT Spice. Okay, so it's not, the learning curve isn't like this when you have to actually do something. Okay, so then it's a DC, and I can come down here. And then right click on that bad dude, 100U, 100U, set the spice model, PMOS, what's it called? P underscore 1U. Okay. And now this is going up to 4 volts. That's kind of close to 5. It may go out of strong inversion. So I'm going to drop this bad dude down to just what I said, 0 to 1. Now, just out of curiosity, this is a PMOS device. What we had before was an NMOS device. How do we expect the capacitance of the two to change between PMOS and NMOS? It shouldn't. It should be exactly the same because we have exactly the same oxide thickness. Where we get confused is when we talk about mobility and IV characteristics and all that, but the capacitance is exactly the same. So let's go ahead and poke the running man and go over here. Nothing succeeds like success. Why is that so slow? Let's put a maximum step size of 10 picobabies. Save, run. What the heck am I? Oops, you know what? I don't know what I was doing before. Delay, rise time 200p. I'm gonna whip some magic out. I guess it's good. Dot options plot. If I was a student, I'd be like, what the heck is he doing? Plot win size equals 0. This, what happens is, this program was made for simulating switching power supplies. And switching power supplies have the unique characteristic that really fast things are happening on short time scales, but the switching power supply operates on a long time scale, and in order to keep the simulation data and response short, they play some games with the plotting and what they store. In order to avoid that, you can put this options in there too, so it doesn't put that stuff in. And so there, now you see the step response, just in case you had that issue. Okay. All right, so what am I going to plot next? V out. And you can see, I guess the time constant's long. Let's hit save. It's 1K. I don't remember what we calculated for this device last time, but I'm not going to calculate it again. Let's just change a sim. Does everybody notice that when I look at this and I hit run, oh, that's one issue. Let's change that back to a millivolt. We're down in the noise. Okay. Does everybody notice that even though I changed the amplitude, it doesn't change the RC shape? Right? So I still have essentially 5 volts across the device. It's still in strong inversion. Okay. How's the pain factor? Pretty high? All right. This stuff's kind of boring. Whoops. We'll talk about strong inversion a little bit, and then I'm going to move on to IV curves. Let's see what's on the old agenda. More MOS, review of RC circuits, frequency response. So what about homework? Okay, everybody see the homework? We went over that already. I guess the thing I forgot to mention was I'm not going to tell you every day, hey, there's homework due a week from today. You'll just get in the groove. Yeah, it's good. Okay, especially since I have a grader and I don't have to grade it. Okay, so you're going to help me on this because the first homework problem has something to do with strong inversion. We're going to do it for the NMOS. So let's sketch the NMOS cross-sectional area. So there's our gate. And what's the material made of the gate? What is it? Poly. Polysilicon, yeah. Okay, so here we go. What I'm going to do is I'm going to plot the capacitance. Let's go C gate against VGS. And so I'm going to ground these. And then I'm going to apply a VGS like this. And I want to get it right to begin with. So let's do the simple part, which is well, you tell me, what's the simple part to begin with? This is VGS. Tell me how to begin. Yeah, so tell me in real simple terms, what can I set VGS to? Okay, that wasn't as simple, but let's say a large negative voltage, all right? So we're over here. Why? Okay, so if I have a negative VGS, what do I attract under here? Yeah, well, let's think of it another way. If I put a negative potential here, what do I repel? When I repel the electrons, I leave behind holes. So I draw holes. Now, refresh my memory. This was called the lateral diffusion. Has the length LD. This distance here was called the length L. Yeah, drawn length. And this distance here is the L effective. Now I'm going to do the same exact discussion when we talk about the PMOS. So if I want to calculate the capacitance, and what goes into the page? The width. So if I want to calculate the capacitance due to the overlaps, start out with the overlaps. Tell me what to write. 2 times LD times W times, yeah, Cox prime. And what's Cox prime? Yeah. The way I remember all of these, if I come back a year later, is I always remember from basic physics, epsilon A over D, or thickness. That's what it all comes down to. The area is the W times the lateral diffusion, and the thickness is the thickness between the gate and the N plus. That's added to L effective, or whoops, I said it and then I wrote it wrong, times W times Cox prime. Yay or nay? And then L is equal to L effective plus what? 2LD. So when I add these together, I get, does that make sense? Which we call, Okay, so the first homework problem that's due a week from today says this is accumulation. Why is it called accumulation? Yeah, accumulate holes. Now, next question. Why is it a bad capacitor area? We got to charge and discharge through this substrate resistance over, so it's not a good cap like this. It looks more like this. Does that make sense? Okay, so we generally don't operate the MOSFET in accumulation if we want a good capacitor. Now let's do the other one, the one I was going to do first, but which is yeah, which is we apply a large positive potential. Let's use orange. Large positive potential here. Looking good? When we do that, what do we attract underneath the gate? But the substrate's p-type. So we change it from p-type to n-type, where we have the electrons. And if we apply a large positive potential, we get a lot of electrons in there. That's called strong inversion. And we can go through in the same analysis, except now the source and drain are shorted together through the electrons. So here's a good interview question. What does strong inversion? Tell me qualitatively, what does strong inversion mean? Yeah, it just means we're changing that from p-type to n-type. So here's another question. So we're inverting it. We're going from t-type to n-type. Here's another question. Do you have to have current flowing between the drain and the source, or drain and source, for the device to be in strong inversion? No. Here's a more tricky question. Can you have current flow in the device without the device being strong inverted? There's no channel there. How are you going to get current to flow? You have to generate that channel. You have to invert the channel. So the answer is no. I got to invert that so I can connect my source and drain together. That's how I get the current to flow from the drain to the source. Okay? If I don't have that channel there, then there's no channel to conduct current. So I have to have strong inversion to get current between the drain and the source. Okay? So let me just put because nothing is absolute, so let me just make a comment. You know your calculators, your wristwatches, all these battery-powered things that last forever, run on solar power? Those operate in what is called weak inversion. And that's the area where it starts to transition, and it looks like this. It's kind of a slow, and then it kind of speeds up and does this. When you're operating in this area, which is weak inversion, and before I continue my thought there, what is weak inversion? Just tell me based upon what we discussed. Yeah, we don't have a lot of electrons there. It's inverted. It's not p-type. We've applied a positive potential. We pulled some electrons underneath there, but not a lot. So there's still the potential for conduction there. All of those calculator circuits and wristwatches and solar-powered things, they all operate in weak inversion, which means they have very small currents. They don't need much power from the solar panel. So they're operating in this area. Processors and your cell phones and that stuff eats power. It operates in strong inversion. The problem with operating in weak inversion, can anybody guess if your currents are nanoamps? Can you guess what the problem is? Yeah, slow. You've hit your solar calculator, and sometimes, especially if it's dark, you're like, come on, you're punching faster than the numbers can respond, right? It's because they're slow. Well, you think about it, why? You have the same capacitances, but now you have to charge and discharge with much smaller currents. Okay? So that's just an FYI. Let's do the PMOS, and then we'll do our RC circuit review. Are there any questions here? Okay, so with the PMOS, I can do it one of two ways. The first way of doing it, of explaining strong inversion, is this. I go and say exactly like we did before, except I have a PMOS device. And I draw the cross-sectional view. Now, in CMOS, all modern processes, or even older ones, they use what's called an N-well to get the body of the PMOS device. And so this is the well, or the body, and that's this right here. Then here is our source, here is our drain, here is our gate. Okay, so let's do it very quickly the first way. Let's apply a positive potential. So we got a positive potential there. And what do we attract underneath the gate oxide? Electrons. What do we say about that underneath the gate oxide? It's an accumulation. Those electrons are the same polarity as the body. They're both N-type. So the surface is accumulating electrons. And we can go through the exact same discussion of lateral diffusion, effective length, all that stuff, and calculate the capacitance to be the same thing as Cox. Let's go with a negative potential over here. What do we attract? Or let's be more exact. When we put a negative potential there, what do we repel? We move the electrons away, right? And that leaves behind holes. Okay? And that strongly inverts the surface. Now I'm going to ask you, has anybody taken semiconductor physics, like the basic introduction? Okay. How about what? Oh, okay. So let me ask you just a couple of simple things. If I have a p-n junction, if I have an n-type and a p-type semiconductor, and I ask you, what is the charge density of that n-type semiconductor? It's filled with lots of mobile electrons, right? Is it positive, negative, neutral? What is it? Okay, so people say it's negative. The problem is you have all these free electrons, right? The way you get that is you add an atom that has 5 valence electrons instead of silicon's 4 valence electrons. Electrically, though, this material is neutral. Just because I have free electrons in here doesn't mean there's a negative potential. Okay? Same thing here. When I make a p-type, I add an atom like boron with 3 valence electrons, and it leaves a vacancy or hole in the valence band. Electrically, it's neutral. Every atom I put in there has an equal and opposite positive and negative charge. So even though I have an abundance of electrons here, an abundance of holes here, they're still electrically neutral. What's interesting is when I put them together. When I put them together, this electron's free to move around. Well, it's going to fall in the hole. Okay? When it falls in the hole, what does it leave behind? The atom's sitting there, it's got all its electrons, and all of a sudden it loses an electron. What happens to the atom? It's positively charged. So it's a positively fixed charge ion. So on this N side here, we get these positive charges. In the P side, we fill up the hole. We have an electron in the hole. What happens? Now the atom's sitting here, oh, I got right charge. Oh, now this other electron moves in, and what happens? Net negative charge. So the P side has this net negative charge. This is what gives rise to the depletion region and the capacitance. And this is part of what's going on here. But one more question before we move on. Why don't all of the electrons from this side move over and fall into all of the holes over here? I mean, doesn't that make sense? When I was learning this, that's what I wondered. Why don't all those free electrons fall over and go into the open holes over here? Well, Yeah, when that atom loses its charge, it says, hey, come back, and it equalizes. So you can't lose too much before there's too many atoms trying to pull the electrons or remove or repel the electrons back. Okay? There's this fixed amount of charge there. The whole point is we talk about electrons and holes, and I said apply a positive potential or apply a negative potential. You repel or you pull forward, attract electrons. You don't change the position of the atoms. Okay? Does that make sense? No? Oh, okay. All right. Any questions on strong inversion? Do you feel like if you've looked at the homework that you can do the first homework without too much trouble? Yay, nay? Okay. No one's going to say yes because they don't want to. No, I said yes and everybody else understands, but I don't. Okay. So let's review RC circuits real quick. What we're going to do, if you want to get ahead when we come back on Monday. Oh, that's one more thing I need to cover. When we come back on Monday, I'm going to cover Chapter 9. Okay, so we're going to move into Chapter 9. So if you want to get a head start, I actually have tutorials online for Chapter 9, so come in and you've already seen it once. Okay. When I see my office hours are at this link, when I travel, which I'll do occasionally, and I don't have office hours, I will put that I don't have office hours here. So there's no need to email me and say, are you going to be in your office? Because if I'm not going to be in my office, I'll put it right here that I'm not going to be in my office, all right? Now, on February 18th, we won't have office hours. That's President's Day, but I'm going to a conference and I won't be here. I might be able to make it back for this class because my flight gets in at like 2 o'clock, but I don't want to take a chance. So what I will likely do is schedule lectures before or after on the Fridays to try to get ahead of ourselves. You don't have to attend the lectures. They'll be online. I won't give a quiz, but I think lecture time is precious, and I don't want you to lose any of it. And so I would rather be very careful about making sure you have your lectures rather than just tossing them aside. Oh, well, we'll get it later. No, we're not going to do that. So, but I'll tell you beforehand. So I will likely be gone Wednesday, February 20th. I'll probably do a lecture the previous Friday and the following Friday, February 22nd. The same exact time, same exact room. That'll get us one lecture ahead so that in the semester when I have to go somewhere, we already have that lecture. We get our what you paid for. Okay. So how well do you guys know RC circuits? Gurus? All right, let me do a simple example and you tell me if it makes sense, okay? Wait, before I do that, let me do an even simpler example that I like to just get a bearing. Let's say the magnitude of V out over Vn is equal to 2. Now let's go 1.2. And let's say the angle of V out over Vn is minus, and let's do what I did before, 60. Okay, so I want to sketch the input and the output of these waveforms in the time domain, okay? So tell me what you would do to begin with. So I could read these directly off of Bode response, frequency response, right? So tell me what to do to begin with. Okay, so why don't because I like really simple things to begin with, why don't I sketch the input? And let's just, to be complete, say this is Vn. What's that? So let me ask you this. When I do a frequency response and I have parameters like this, what can I say about the frequency of the input and output? They got to be the same. I can't compare frequencies at two different. I can't compare the input and output at different frequencies because then phase shift and all that doesn't make sense. Does everybody follow? Okay, so I don't know what the absolute amplitude of this is, but I know that the output's going to be 1.2 times bigger. So I'm going to go up and I'm going to put a plot. Let's see if this is, let's just normalize it to 1. This is 1.2. I don't know what that amplitude is, keep in mind. I'm just going to go 20% bigger. Come over here. Then I'm going to go 1.2. Then let's sketch. Let's see. So I know the output of my circuit is going to swing between those two rails, right? I just don't know where. What do I know about the frequency of my output? Again, it's the same as my input. So if that's T, this is T over 2. Okay, so far easy, right? What does the minus sign indicate? And don't give me something challenging. I want something trivial. Don't say leading, lagging, or unless you make it real simple. Yeah. Well, here's the way I think of it, okay? The way I think of it is that minus sign means the output's occurring after the input. That's all I think of it. If a minus, it's output after input. If it's positive, output before input. If I have a digital logic gate that has a 5 nanosecond delay, would I say that in relation to phase, I would say the output occurs after the input, right? Or it'd have a negative phase shift. Okay, does everybody get that? Negative phase shift, output occurs after input. Okay? All right, but that still isn't, okay, that's fine. But how do I intuitively get there? Okay, if I have a logic gate and I do digital, it's very easy for me to understand delay, right? I look at delay through a gate, I know what that is. What phase shift is it's a delay, delta t, as a percentage of the period. So that's the way I think of it. Times 360 or 2 pi if you want to use radians. And that's the how I get phase shift. So if I ask, if here's my input and I'm comparing this point with my sine wave here, let's see, I used red. What's the phase shift from here to here? What's the delay? If I go between here and here, what's the delay? Well, no, what's the delay from here to here? T over 2. If I plug that T over 2 in for my delta T, what's my phase shift? Somebody said it, lots of people, 180. If I have a 60-degree phase shift, then I go over 1/6 of the period to T over 6. So let me see, just to be, because I'm a horrible artist. So that would be T over 4. This would be T over 8. What's T over 8 correspond to in phase shift? A delay of T over 8. 45 degrees. T over 4 is 90 degrees. So I go, well, I got 60. That means my 0 point is going to be right about, let's see, 90. It's right in the middle, just about. Okay, right there. So I can go draw my sine wave now, and let's just, because I'm a horrible artist, I need all the help I can get, handicaps. Let's see. Okay, so before I draw the sine wave and complicate things, what's this delta t? It's T over 6. So I plug in T over 6. What do I get? 60. And the minus I don't worry about because that just means the output occurs after the input. So I go, all right, now let's see how horrible I can draw this. Let's see. Let's see. See, I told you I'm horrible. Yeah, well, I probably would have I could probably calculate more points in here and draw it a little better, but you get the idea. So the delay, I could also use these peaks, couldn't I? Well, if I drew them a little better, because they would be spaced apart by t over 6, I could use these zero crossing, or I could use these two peaks. I just have to pick the like points. What if I picked this peak with this peak? What would happen? So if I continue drawing over here, I'd have a peak here and a peak here. If I ask what's the phase shift between the input and the output here, is it positive or negative if I compare these 2 points, like points? It's negative. This point's occurring, the output is occurring after the input. Okay? What if I compare this point with one of the outputs over here? Positive, because then, but what would also happen if I did this? The phase shift would be over 360 because the time delay is over t. Okay, so the key points, if you take away anything here, negative means output occurs after input. Positive means output occurs before input. You can throw the leading and lagging in there. Negative means output lags input. Negative means input leads output. I mean, it's really confusing, right? That's why I like output before, output after. And if it's positive, you flip it. And then the delay is just the percentage of the period. That's the way I remembered. I never remember the equation. I always remember, oh yeah, delay is just the percentage of the period. Okay? All right. Let's move on to an RC circuit. So let's do what you've already done, and I'm going to just talk about it, and we're going to sketch the Bode response, but I want to make sure we're on the same page here. So this is R, C, and we have, this is a sine wave now, Vn, V out, and that is, so what's the impedance of the capacitor? And so if I do a voltage divider, V out is equal to Vn times 1 over SC divided by R plus 1 over SC, or V out over Vn is equal to 1 over 1 plus j omega RC, where S is equal to j omega. Is anybody not seen this before? Has anybody seen this before? Let me ask that. A few people. Okay. I'm going to change this a little bit. I'm going to write plus J0. So I have a real, imaginary, real, imaginary. Now, just real quick, if I'm in the complex plane and I've got a y component, this is my imaginary axis. This is, I really cringe when I cover this because I think most people don't understand it, including professors, but this is a vector in the complex plane and it represents, say, a sinusoid. What does that mean in your mind? Yeah, but what intuitively, why do we use the complex plane? What's the deal? Well, we want to talk about time delay. And in reality, what happens is this isn't a steady vector. It's a vector rotating around and around in the complex plane. And using imaginary numbers lets us put time into things. Okay? So we take this snapshot here, but it's actually rotating around and around. All of the sinusoids in the circuit are rotating around and around. And how long does it take for it to rotate, one of the sinusoid signals, whatever it is, to rotate around? 1 period. So when I use this representation, it assumes I know the frequency and that they're rotating around. Okay? And if you want to know more, in my red CMOS book, I derive how J is used and all that, and I'll print out those copies, but you're going to have to ask me because you may not care. All right, so this is X, and let's just say A equals X plus JY. And then the magnitude of A using Pythagorean's theorem is the length, and that's square root of x squared plus y squared. What's this angle? tan inverse, but it's positive, right? Because it's, and notice in this circuit here, the only a number that we have in the form of a equals x plus jy. Did I use I? Holy cow. That's a senior moment. Anyway, jy is the top one, right? So I'm going to take the magnitude of V out over V in and just do the top portion first. And that's equal to the square root of 1 squared plus 0 squared, which is 1. Whoops. Does everybody agree with that? But I don't have, this number isn't in that form. How do I get it in this form? Now, I'm going to really blow through this because we don't have the time. The way I get it in the form is I use the complex conjugate. So I multiply, if I have a number like C plus JD, 1 over that, the way I get it into the form that it's like this is I multiply times the complex conjugate. And then I get, what ends up happening is I get that the magnitude of 1 over C plus JD, and again, this is in my red book. If you want, I can bring it in, is the square root of C squared plus D squared. And the angle is minus tan inverse of y over x. So it's just 1 over the magnitude and then negative. Anyway, so when I take the magnitude of this, I get, and we'll move on, to 1 plus 2 pi FRC squared. Okay, so you've all seen this before, so I'm going to focus on this. I don't want you to have too little time to do your quiz. Don't worry, we'll have it. Even if we have, no, I won't inconvenience the next person. Okay, so we have this now. Let's just look at this. V out over V in is equal to 1 over the square root of 1 plus 2 pi FRC squared. And the angle V out over V in is minus tan inverse of 2 pi FRC over 1. What is the angle of the numerator here? 0. So it's tan inverse of 0 over 1. So I could be complete instead of lazy and put 0 here, but I was being lazy. That's from the numerator. Okay? Looking good? Okay, so I got a question. What's the deal with the 3 dB frequency? I mean, it took me years to figure out, why do they keep talking about this thing? What's the big deal with the 3 dB frequency? In fact, if I go look at this and I say, what's the 3 dB frequency? Well, everybody would tell me, and I'm sure you all know, is when F is equal to what? Okay, did anybody else know that besides a grad student that took a graduate class in low noise from me already? Did everybody know that? Because I'm starting to think maybe on Monday I need to go over RC circuits in a little more detail. Did anybody know that? No? Have you seen this before?
It was like a footnote somewhere.
What? Oh no. Wait a sec. So if I plug this F in here, let's just leave it, we won't say F3dB, we'll just say F equal 1 over 2 pi RC. This was the real part. This was the imaginary part, correct? When I plug the F in there, I get 2 pi over C, RC divided by 2 pi over RC. What does that term, the imaginary part, become? 1. At low frequency, say F is 0. What is this part? 0. The thing about the 3 dB frequency is when the real part and the imaginary part become equal, that's when the imaginary part's starting to grow bigger than the real part. That gives you 1 over root 2, which is 0.707, which is minus 3 dB down. So it's an arbitrary number you just plug in here. It's when the real part and the imaginary part are equal. Does that make sense? Okay, be honest with me. Do we need to cover this in more detail? Because I'm going to I'm blowing through this, and if you don't get it, when I start throwing up, here, let me show you some examples. When I start throwing up, let's see, where's a good compensation? Here, look at this page. This is a chapter we'll cover in not too long. Here's a derivation in frequency response. If you don't know what a zero is or a pole is, or why we write it in this form right here, 1 over j plus f over f sub s, so I can say, well, if this is f3 dB, I can go write this term as 1 over the square root of 1 plus f over f3 dB, because when I plug in f3 dB, I end up with that equation. If you don't know that, I don't want to continue charging on. I want to cover this. This is important. Do we need to cover it? Okay, so we'll do that on Monday. So let's continue with this example, and we'll plot it and all that. Well, let me ask another question. Have you looked at decibels very much? dB? Log? Why do people use logs? Logarithms. It's a way to just, okay, let me say, let's say I have 1,000 volts. Okay? Let's say I have 1 microvolt. If I try to plot those on the same plot, this is what it's going to look like. 500 volts, 1,000 volts, and then here's my 1,000 volts. Here's my 1 microvolt. I can't see if it's 1 microvolt, 2 microvolts, 3 microvolts, whatever, right? Okay. Logarithms let you plot big numbers and small numbers on the same plots. So if I take the log of this, let's say I do 20 log of 1,000, which is what? 60 dB, because it's 10 to the third. Log of 10 is 1. We bring the 3 down. If I do 20 log of 1 microvolt, which is 10 to the minus 6, I get minus 120. And I go on a plot, and I go from minus 200 to plus 100 dB, because these are now dB. I can put my minus 120 right here, and I can put my plus 60 up here, and I know, hey, that's 1,000 volts. Hey, that's a microvolt on the same exact plot. Does everybody follow that? Okay, so when we talk about dB and we're doing all these Bode responses, when this f starts to get big, drives this term to what? As f gets really big. 0. Well, it's going to get really, really small, but if I want to compare it to 1, it's hard to do it on a linear plot. If I plot it linearly, it looks like this. If I plot it with a dB plot, we're going to see it looks like this, and I can go down to really tiny values and still see what the value is at a specific frequency. One more thing, and then we'll continue on with this. What does decade mean? Did you cover it? I know you know. What's decade mean? No, simple. Let's do it real simple. Like, what does negative phase shift mean? Output after the input. Okay? Why do we use logarithms? Big things and small things together. I'm keeping this simple. I'll watch the video tonight. All right. So when we talk about decades, and we'll do that when we talk on Monday about the Bode response and all that. When we talk about decades, that means either times 10 or divide by 10. What's 1 decade above 1 kilohertz? It's 10 kilohertz. This is like whenever you use multiplication, second grade or whatever. This decades means multiply by 10, divide by 10. So if I'm at 123 hertz and I say, what's the frequency 1 decade below 123 hertz? It's 12.3 hertz. You just divide by 10. Multiply by 10. What about octaves? Don't say 8. It's a double. It's multiply by 2, divide by 2. If you've done music and you go up an octave, that means you're multiplying your frequencies by 2. You go on your piano up an octave, your frequency changes by a factor of 2 of everything. So what's one octave above 123 hertz? 246. Okay, let's if we say plus 20 dB or minus 20 dB, what does that mean? Times 10, divide 10. So if I have a gain of 20 and I run it through an amplifier with a gain of 20 dB, what's my gain now become? 200. Just multiply by 10. Okay, or divide by 10. And 6 dB is, I say this right at the beginning because once we start talking about all this stuff, it's really simple, but then we get lost in the math. Okay. Any questions? I got a question. Here's another useful one. This is how I remember all these. What's 14 dB? 5. So what's 34 dB? Multiply by 10, multiply by 5, 50. What's 6 dB? And of course, minus 14 dB is what? Divide by 5. What's 6 dB? 2. All right, so the big one. What's 3 dB? What's minus 3 dB point? Man, I really need to get that monitor down here. That's distracting. I got a cable. We'll hook it up that way next time. So what's the point of this? When the real and the imaginary parts are equal. It's all simple. Once you understand it, that is. Okay, that's your 3 dB point. That's when the gain is 0.707, minus 3 dB down, 20 log of 1 over root 2, just to be complete. Okay, let's plot this and then quit for the quiz. So let's plot this to begin with. So 10. So we're going to plot the magnitude V out over V in, which is 1 over the square root of 1 plus 2 pi RCF squared. I'm going to rewrite it with F 3 dB equal to 1 over 2 pi RC as 1 over the square root of 1 plus F over F 3 dB squared. Okay, does anybody disagree that if I plug F 3 dB in here, that I'll get exactly this equation here? Just plug this into here, flips up, and I get the exact same equation here. Yay? Okay, so let's do 20 log of V out over V in, which is 20 log of 1, and this is the magnitude, the square root of 1 plus F over F 3 dB squared. I'm going to be verbose here. Not that I'm not already verbose. Everybody agree with that? because the 1/2 comes down. And now I say, I didn't leave myself much room, but I'm going to plot the magnitude. For F, let's draw F3dB, whatever it is here. This is the magnitude. For F, much, much less than F3dB. For frequencies, much, much less than F3dB. What can I say about this? Yeah, this is negligible, and I get log of 1, and I get 0 dB. So I'll just go up here and I'll put 0 dB. When F3dB, when F is equal to F3dB, what is this? Yep, 2. So log of 2 is roughly? What's that? Well, okay, so if F is equal to F3dB, this is log of 2, right? So what's minus 10 log of base 10 of 2? We already went over it. When F and F3dB are the same, log of 2 is times 10 minus 10. 3 dB minus 3 dB. So I go up here. This is why they like it. So it starts rolling off. And yeah, that's supposed to be there. I'm a horrible artist. Okay, and then if F is much, much greater than F3dB, this term just essentially goes to F over F3dB. We can use this. We'll come down here. And if this is the case, we get minus 20 log F over F3dB, which if F is increasing, what does that mean? The minus sign. It keeps getting bigger and bigger and bigger. It just rolls off like this. And we'll do this on Monday in detail. It rolls off for every increase in 10, we get a decrease in gain by 10. So for every increase in 10, what would be 1 decade above F3dB? I'm the king of trivial questions. What's 1 decade above F3dB? 10 F3dB. Well, if it's rolling off, an increase in 10 causes a decrease in 20 dB of decade, that this goes from here to here is 20 dB decrease. So for every 20 dB decrease in gain, we get a times 10 increase or decade increase in frequency. But we'll cover this in detail on Monday, and I'll assign some homework so you get practice, and we'll do some sims and all that. All right, let's pause and